We know how to calculate the potential due to a sphere, due to point charge, or even due to a ring. But now we are going to study the potential by the electric dipole. Dipole, a system of two equal opposite charges. For this, we consider two positions. First of all, the position will be that on the axis known as axial position, like this one, minus plus charges. If you consider a point at a distance r from here, this point, at this point the potential because of q is going to be positive, it's a positive upon r minus a, and that too due to minus q it will be minus, and the distance will be r plus a, potential because of both the charges. Since both are opposite in nature, to sum up, we find q common, and this will be 1 r minus a, r plus a. You take the LCM, it's difference of the square. It will be r plus a over here minus r plus a. It's going to be 2a, and here it's q. What remains is 2qa, that is p, 2qa. 2qa you could write directly p upon r square minus a square. It is the potential because of a dipole at a point that is lying on the axis and at a distance small r. You see, when we say the distance from some object, some body, it simply means the distance from middle or the CM. For dipole, CM is going to be here. From here, you consider the distance. And if you consider SI, simply this would be multiplied 1 upon 4 pi epsilon naught P upon R square minus A square. That becomes the potential. Now let's consider another position that we known as transverse position. Transverse. It simply means the dipole is in a position and on its perpendicular bisector. The point is lying on the perpendicular bisector. It's optional. You might choose the point in any side. And suppose the distance from this dipole is r. Again, the distance from midpoint. Suppose it is r. Both the charges are equidistant. They are at the same distance. They are having the same value. Then they will obviously produce the same potential, because this distance and this one both will be equal. It is on perpendicular bisector. So from that point of view, plus V1 minus V2, that becomes the total potential. V1 you might consider because of one charge, V2 you might consider because of the other, but both are equal and opposite. That's why the net potential shall be equal to 0. In both the position, we got the values. It's unlike field. One more thing you must know, you see, if you want to find the potential because of the two charges, quite in the middle, then in that case again, this point is going to be equidistant and the potential will be 0 over there. Now, we want to know if a dipole is placed in some electric field. In the electric field, it might have any angle. We suppose here the angle of the dipole is theta. You know, the dipole is considered as a vector. Its direction is always taken from minus to plus. Just suppose this angle is theta. Dipole is having two charges And even if a single charge is placed in some electric field, it does have the potential energy because of the present position. Likewise, here the two charges being placed inside the electric field, they must be having some potential energy. And their total energy would be termed as electropotential energy of dipole. The electropotential energy of dipole, when it is placed at angle theta in electric field, might be given by this relation, minus P E cos theta. You could say it's a scalar product of P and E. This angle is variable. You can assign any value to it. If it is 0, it simply means the dipole is parallel to the field. In that case, cos theta is going to be maximum. When you put this value maximum, you'll get here U minimum. This is minus PE. The most stable position of the dipole, you must remember, when any system, any body has the minimum potential energy, it's likely to be stable. And when a dipole is allowed to be suspended in uniform electric field, it will always try to be in stable equilibrium. That means it will always try to be aligned or along the electric field. At the same time, if you consider the angle is 90 degree, cos 90 0, you will be 0 in that case. And if you consider this 180, it will minus 1. And in that case, U maximum, that's going to be plus E. This equilibrium, obviously this will also be equilibrium, but in this case the dipole is going to be in unstable equilibrium, means a little jerk, a little disturbance, and this will permanently disturb itself. When the potential energy is 0, it is said to be in neutral equilibrium. And with that, we have covered even electropotential energy also. Now, only thing left for the dipole is, like two charges, when they are at a certain distance, they apply the force on each other. That's known as electrical or Coulomb force. Similarly, if there are two dipoles, you see, you could arrange the dipole in at least 4 manners like this. Both are parallel, pointing same direction. Both are parallel, pointing opposite direction. Both are parallel, same direction. Both are anti-parallel. But we have chosen here only two cases. In one case, you see the dipole is here this way, P1, P2, and they are having the distance R. In this case, the force between them is going to be, this is what we are talking about, CGS system. For converting into SI, just multiply it by 1 by 4 pi epsilon naught. But this is equal, not proportional. I am sorry for this. It is equal. Similarly, if there are two dipoles pointing the same direction and parallel to each other, in that case, the force is going to be exactly half of the value above this one. The point to be underlined or to be noticed is that here the force is directly proportional to fourth power of distance between them, whereas in the case of point charges, you must have noticed that force follows inverse square law.